Teacher Carlos, a plane of Durham School, states, "Totally, I went through my entire time on Earth empowering an express hypothesis of the universe. Additionally, at last, the hypothesis is being tried. I welcome that since that is the manner by which we push ahead, that is how we gain ground in science. The James Webb Space Telescope is upsetting an extraordinary measure of what has been seen as truth in cosmology. For the new year, another ultra-deep image shows that we have made serious goofs in cosmology. The telescope that was supposed to show us the universe's earliest stars is evolving into an adversary of the past perspective. Furthermore, it may present to us a thoroughly astounding science. Not all experts are railing in dread at the new realities. Other well-informed specialists welcome the changes because it has, for a genuinely extended period, been clear that something was amiss with our old hypotheses. The deviation in the assessment of the progression speed of the universe alone should have shaken scientists' beliefs long ago. Yet, instead of reevaluating, they clung to outdated theories. The galactic microwave background radiation, CMB, considered the oldest light in the universe, was created about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. Researchers call this process reionization, which made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of radio antenna technology. This discovery was long considered one of the strongest pieces of evidence supporting the Big Bang theory, earning Penzias and Wilson a Nobel Prize and an undeniable place in the history of astronomy. The CMB most reasonably provides a glimpse of the early universe, with small temperature differences offering essential data about conditions shortly after the Big Bang. Specialists included the CMB as a crucial aspect of fundamental assessments of the universe to calculate the expansion rate, among other things. Cosmologist Edwin Hubble had already settled the expansion concept in the late 1920s, finding that faraway galaxies retreat from us at a speed proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. However, Hubble didn't have access to the advanced measuring techniques available later. When the CMB was discovered, recalculated expansion rates were considerably lower than Hubble's original estimate. Later, experts recalculated the rate using Type Ia supernovae as standard candles, producing stable light that could serve as reliable reference points. Estimates derived from the CMB indicated an expansion speed of about 67 kilometers per second per megaparsec, while those using supernovae suggested around 74 kilometers per second per megaparsec. What does this discrepancy in the universe's expansion rate truly indicate? Did you know that this inconsistency has been known since the 1990s? Since then, researchers have suspected that something may be wrong with the evaluation of the CMB, the assessment methods, or even the concept of the universe's expansion. This anomaly between observed and predicted values of the expansion rate is referred to in science as the Hubble tension or SAA strain. The implications of this strain are vast, suggesting that fundamental aspects of how we understand the universe might be flawed. For decades, researchers were frustrated. But since the James Webb Space Telescope, JWST, became operational, it has provided astonishing data that may finally address the issue of the universe's expansion speed. Some systems are so ancient and developed that their formation theoretically predates the Big Bang, upsetting long-held cosmological assumptions. Experts no longer talk about errors or discrepancies. They discuss a full-blown crisis in modern astronomy. Not only might the expansion rate be incorrect, but the entire concept of the Big Bang itself is being called into question. Images from the telescope reveal a universe entirely different from what we've long believed. The Hubble tension was the first warning for those who still held faith in old theories. Now they face a bigger issue. Do we truly understand the universe? Other scientists stand amidst the ruins of their once proud foundation of discovery and struggle with fear as they investigate space and grapple with what they uncover. Given this crisis in science, we must ask ourselves, what do we truly know about the universe? To answer this, we need to understand how science operates. Theoretical experts utilize a sophisticated arrangement of mathematical models, meticulous data, and analytical reasoning to derive conclusions from the general to the specific. Their understanding emerges from a combination of observational evidence, experimental results, and theoretical evaluations. The term theory itself indicates that these are frameworks and concepts, not absolute facts. The primary substantial data we possess include images provided by telescopes, sound waves, and radiation gathered via radio telescopes, as well as recent information from neutrino observations or gravitational wave detectors. With the James Webb Space Telescope, JWST, we now have an instrument capable of splitting light into individual frequencies and analyzing it in unprecedented ways. JWST can reveal the fundamental properties of galaxies in the early universe billions of years ago, including their mass, the number of stars they contain, and the paths of their development. However, JWST has limitations. For example, it cannot always definitively determine whether we are observing galaxies or black holes with immense gravitational forces radiating as brightly as galaxies. Could it be that scientists missed critical misinterpretations? Or might our telescopes themselves be flawed? Dark matter and dark energy sit at the top of the list of suspects in this cosmological crisis. Our evolving models of the universe incorporate concepts suggesting that dark matter and dark energy comprise approximately 95% of the universe. However, neither has been clearly observed, nor has their existence ever been definitively proven. It's plausible that they don't exist in any tangible form, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. Conversely, they might possess properties we have yet to understand. One idea is that the characteristics of dark matter and dark energy may have changed over time, potentially indicating some form of evolution. Gravity is another theory under scrutiny. This force, which causes attraction through mass or spacetime curvature, remains incompletely explained. Einstein's concept of spacetime curvature, while groundbreaking and widely supported, may need revisiting. It's also possible that gravity exhibits unexpected properties, or that an entirely new force is responsible for the gravitational pull between objects. Over time, several constants have been established in cosmology and astronomy as universal principles. However, the study of the universe has always been a journey defined by our relentless pursuit of understanding and discovery. From ancient civilizations observing the stars to modern space telescopes exploring the depths of the cosmos, every step forward in theory and technology has unveiled new mysteries while challenging established beliefs. We must confront the reality that our science has long accepted far too many probabilities as facts while dismissing alternative explanations. Research has often operated with an overconfidence in its precision. The latest discoveries from JWST serve as crucial clues to replace outdated theories with fresh insights, as has historically occurred in science. Researchers eagerly anticipate new revelations that are unexpectedly surprising. Meanwhile, other experts are striving to develop new explanations. These recent discoveries shake the foundations of our current science, unsettling many experts. The prevailing models of physical science still largely rely on Isaac Newton's laws from the 17th century. His principles of motion and gravity formed the foundation of our understanding of the physical world and the universe for centuries. Newton's laws explain the movement of objects under normal conditions, particularly on Earth. However, in space, his theories required refinement, which was achieved primarily by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, revolutionized how we interpret reality, demonstrating that space and time are relative to each other and dependent on the observer's motion. His general theory of relativity, published in 1915, expanded this concept with mathematical descriptions of gravitational properties, explaining the curvature of spacetime caused by massive objects like stars or galaxies. Einstein's theories and ideas were transformative across many fields, yet he, too, recognized their limitations. He understood that his theories could never fully describe the universe and yearned for a unified theory, a goal he never achieved. No other scientist has reached this milestone either. Wouldn't it be fascinating to discover where the truth lies? Michio Kaku, a prominent astrophysicist, noted in an interview that solving this mystery would undoubtedly earn a Nobel Prize in the realm of cosmology. The James Webb Space Telescope, JWST, stands as a testament to our scientific advancement, poised to transform how we perceive the universe's origins and development. Launched with unparalleled capabilities, JWST marks a leap forward in observational astronomy, designed to delve deeper into the universe than ever before with unmatched precision in analyzing radiation. The cosmic microwave background, CMB, often referred to as the afterglow of the Big Bang, provides a glimpse into the universe as it existed only moments after its inception. This ancient form of radiation holds critical clues about the early universe's conditions, including its temperature variations, which are essential for understanding the evolution of galaxies and large-scale structures. However, the discrepancies in determining the Hubble constant, known as the Hubble tension, have long been a topic of heated debate. This tension suggests that something is fundamentally flawed in our understanding of the universe and its foundational structures. JWST's observations may provide the key to resolving these discrepancies by offering unprecedented insights into cosmic development. These revelations challenge traditional theories and force us to reconsider whether our perspective on universal evolution is fundamentally flawed. New insights could unveil hidden aspects of the universe's formation, raising questions about dark matter and dark energy, two enigmatic components that constitute the majority of the universe's mass and energy. The progress of science relies on its ability to adapt theories in response to new information. JWST's mission exemplifies this pursuit, and its discoveries promise to become the cornerstone of future cosmological discussions. These findings are likely to inspire fresh perspectives on the universe's mysteries. The future of cosmology might witness transformative changes, leading to profound implications for how we interpret the cosmos. From the Big Bang to the ongoing processes shaping its destiny, the answers to humanity's most profound questions may lie beyond our current understanding. JWST's observations might eventually provide pivotal insights that redefine our perception of reality itself. The journey ahead for cosmology and space science is fraught with possibilities. Every observation and data point collected from instruments like JWST brings us closer to answering the most fundamental questions ever posed by humanity. How did the universe begin? What is its ultimate fate? Are we alone in this vast cosmos, or do other forms of life exist? As we advance further into the unknown, one thing remains certain. Science, much like the universe itself, is in a perpetual state of expansion, driven by curiosity, discovery, and the insatiable quest for knowledge. Every revelation opens new doors, and the road ahead is illuminated by the promise of discovery. As the JWST continues its mission, it not only serves as a window into the universe's past, but also acts as a beacon guiding humanity's future exploration of the cosmos. With each breakthrough, the narrative of the universe unfolds further, reminding us that our journey through science is an endless odyssey of wonder, knowledge, and transformation.